third speaker, Phil Mansfield, actually isn't here, and it looks like he isn't coming. So we can be a little bit more relaxed on the timing of this session.
Thank you, Joe. Test.
So the first speaker is Fangzhou Jiang, and he's going to be talking about the non-correlation between spins of galaxies and the lambda of the host halo.
Thank you, Joe, for inviting me back. So I'm Fangzhou Jiang. I'm a postdoc at the Hebrew University of Jerusalem. Today, I'm going to tell you that there is almost no correlation between galaxy spin and host halo spin. And to some extent, galaxy sizes do not care about halo spin parameters at all. This is a work mostly done at the Hebrew University of Jerusalem with Avishai Dekel and our collaborators. Many of you are sitting here today. A common sense of galaxy formation at high redshift is that baryons and dark matter feed to galaxy growth following similar filamentary structures. So on the large scale, they feel the same tidal torque. So we can expect at the moment of viral radius crossing, the gas-specific angular momentum is comparable to the specific angular momentum of the dark matter. For the same reason, for the past 20-ish years, people have been assuming in semi-atomic models that the specific angular momentum of the galaxy is comparable to that of the halo. And this is a very convenient assumption to make because it allows us to relate galaxy size to halo's viral radius by this formula. So this assumption, together with the assumption that galaxies have flat rotation curves, essentially means the first factor is unity, the third factor is also unity, so the relation between galaxy size and halo size is only via this factor in the middle, which we call the halo spin parameter. There are two pieces of indirect evidence for this assumption and for this very simple galaxy size recipe. Number one is that galaxy spin and halo spin follow very similar log normal distributions. And number two, the galaxy size distribution obtained in this way agree very nicely with observation. So what we do is actually very simple. We want to test this assumption and this galaxy size recipe directly using cosmological hydro simulations. And we use two simulations in particular, Vela and Nihao. The two simulations have been introduced multiple times, so I won't mention the details, but I just want to emphasize that they differ very much in the code, in the resolution, and in feedback. So Vela has much better resolution, but Nihao have much stronger feedback than Vela. The striking thing is that the moment we plot galaxy spin versus halo spin, we see no correlation. To confirm you, we have 0 correlation coefficient, and a linear regression shows a flat line. We can bin our sample into redshift bins and halo mass bins. So on the left-hand side, we have redshift between 1 and 2. On the right-hand side, we have redshift between 2 and 5. Upper rows, halos more massive than 10 to the 11.4. Lower panels, halos less massive than 10 to the 11.4. So we see no correlation at redshift higher than 1 in each of these mass and redshift bins. And there seems to be a systematic trend that in more massive halos, the galaxy spins are higher. And later, I will show you clearly this is a galaxy compaction effect. Similar lack of correlation is seen in the Nihao simulation, and because Nihao runs to redshift 0, we can see that there seems to be a weak correlation developing towards lower redshift. But if I remove this line, this regression that guide your eyes, we are left with a scatter plot, which is very hard to say if there is a correlation, right? So the puzzle is, how do we get from the nice correspondence at info to the non-correlation that we observe? To help us think, we can just simply parameterize the galaxy spin parameter as a product of the halo spin parameter times the spin ratio. This spin ratio basically captures the change of the spin with respect to that at info. And we just assume this spin ratio may depend on halo spin, and we assume on average that the spin ratio scales as the halo spin parameter to a power of b. That's how we wrote down this regression line. Our finding showed in the previous slides are basically B is -1 at high redshift, and B is between -1 and 0 at low redshift. It's quite trivial, and it basically says we need some mechanisms for high spin systems to lose specific angular momentum, and maybe for low spin systems to increase their baryonic specific angular momentum. And we can think of two such mechanisms. One is galaxy compaction. So we can consider a system that starts with low halo spin and therefore low gas spin. Low gas spin basically means gas feeds to center very fast, right? And we increase this inner surface density to have a galaxy compaction. And then when the blue nugget forms, we have high central star formation rate and very quick gas depletion. And then later, freshly accreted gas with high spin parameter forms a ring on the outskirts of the blue nugget. And it is the ring that dominates the spin of the end state of the system. So we started with a low spin system, and we end up with a high spin system. This simple picture is confirmed at least in the Vela simulation. So here I plot on the y-axis spin parameter of the gas, and on the horizontal axis the scale factor. So all the Vela galaxies are stacked at the moment of their main compaction event. And you can see this significant increase in the gas spin parameter post-compaction. And by the way, at least in the Vela simulation, compaction happens at the characteristic mass scale, which is a virial mass of 10 to the 11.4-ish. So this trend of increasing lambda gas is basically a mass trend. The second mechanism is merger, and in particular, halo mergers followed by galaxy mergers. Consider a halo merger. During the merger, the halo spin parameter will temporarily rise simply because the satellite galaxy's orbital angular momentum dominates the halo spin parameter. And at this stage, the galaxy spin parameter doesn't change because the galaxy sits at the center, doesn't feel the halo merger yet. After a couple of dynamical times, the halo revirializes, so the halo spin drops, whereas the galaxy spin will rise for the same reason, because now the satellite galaxy makes it to the center and start to dominate the galaxy spin. So between halo merger and galaxy merger, we have high halo spin, low galaxy spin, and immediately afterwards, the opposite. This simple picture is also confirmed in the simulation. So here I plot the spin ratio normalized to unity at the moment of the halo merger as a function of time after halo merger. So you can see that for the first couple of dynamical times, the ratio decreases, and then afterwards it increases. So we can remove the snapshots immediately after halo mergers, and indeed we recover a weak correlation, but still quite weak. All right, there are other possible mechanisms that can randomize the spin-spin correlation. I won't mention them in detail for the sake of time. I will refer you to this nice paper by Danovich et al., which nicely summarizes this 4-stage angular momentum buildup of high redshift galaxies. So the settlement of galaxy angular momentum is a very complicated process. So at the end of the day, you won't be very surprised by the lack of correlation between galaxy spin and halo spin. But maybe there is correlation between the galaxy spin and the inner halo spin. So here is how I check it. So I plot the correlation coefficient between galaxy spin and the dark matter spin measured out to radius r as a function of radius r. So you can see that there is pretty much a pretty strong correlation between galaxy spin and dark matter spin out to at least 0.2 RVR, and especially at lower redshifts. This is also seen in the Eagle simulation, where they follow Lagrangian volumes. How about alignment? The alignment is always good between galaxy spin and halo spin. On average, if we plot the distribution of the cosine angle between the galaxy spin and halo spin, we find the cosine value is 0.7-ish on average, which means that half of the systems have the spin vectors lie within 45 degrees. So the mechanisms that smear out the spin-spin correlation should not randomize their alignment too much. And also, there is a weak trend that the alignment weakens slightly towards lower redshift, which is also seen in the illustrious simulation. So back to the galaxy size recipe. We can directly check it by plotting the 3D galaxy effective mass radius over the galaxies, over the halo virial radius as a function of halo spin parameter. You won't be surprised that there is almost no correlation. So the symbols here represent the medians, and the arrow bars indicate the percentiles. The colors differentiate different redshifts. The dashed line here is the abundance matching results obtained by Somerville et al. Earlier this year. So you can see they're mismatched, right? Here is flat, here is a one-to-one correspondence. I want to emphasize, though, abundance matching doesn't give you this functional form. So what this dashed line says is basically, if you have to use this galaxy size recipe, then the proportionality factor you get is 0.5. Okay, so despite this non-correlation between the size ratio and halo spin, we can plot galaxy size versus halo size, and we still see a very nice correspondence. This may be at first glance very trivial because you expect larger galaxies to live in larger halos. But the normalization is interesting. Also, the scatter is interesting. You can see that the Vela galaxies, especially those lower redshift Vela galaxies after compaction, they settle almost spot on this local empirical relation obtained by Andrei Kraftov. Also, this scatter of 0.5 DAX have been used as an indirect evidence supporting the relevance of lambda halo, because 0.5 DAX happens to be the width of the log normal distribution of lambda. But here I show you directly that this scatter is actually the scatter in the y-axis here, in the size ratio. It has nothing to do with the scatter on the horizontal direction. Okay, so this recipe is at least questionable in the Vela simulation. The Nihao simulation tells us a different picture. We see some correlation here between the size ratio and the spin parameter, but the Nihao galaxies are oversized at this sub-L star regime and kind of too compact at this Milky Way regime. So I want to mention that this non-monotonic behavior is kind of universal in many recent hydro simulations with very strong feedback. So there is something we don't know for sure yet, how to implement the feedback to, at the same time, reproduce the stellar halo mass relation and the size mass relation, or the size halo size relation. All right, I hope I've convinced you that this factor is almost random. And I think Michael have told you the other day that the galaxy rotation curves are not necessarily flat. So in writing down this formula, at least two factors are not unity. So we should put a big question mark on this relation. So now we are in a situation that lambda halo may be irrelevant, and the galaxy size halo mass and the galaxy size halo size relation is not universal because of, I showed you there is a kink when the compaction happens. So the question is, can we still get galaxy size using halo properties alone? Can we still do semi-elliptic models, in other words? And I think the answer is yes. Interestingly, we find that galaxy size scales almost linearly with the NFW scale radius of the halo. And we can ask another question, which is, are there any secondary halo parameters that may tighten the galaxy size halo size relation? And I think we do. We have, like here, I color code the data points using halo concentration parameter. And on the right-hand panel, the same plot, but different color coding by the industrial shape parameter alpha. And you can see nice color trends. So we can put in the scaling of concentration, and we can tighten this galaxy size, halo size relation further. Okay, so before I summarize my talk, I want to advertise two loosely related projects. Last year, I demonstrated to you that halo substructure statistics can be studied using a very computationally lightweight semi-elliptic model. And this model, which we now call SAT-GEN, was used in a series of papers by Jiang and Vandenbosch. And in a nutshell, this model is basically EPS merger trees plus very simple dynamical evolution recipes for the substructures. We are now trying to upgrade the model to also include halo response, and maybe we want to apply subhalo abundance matching or some kind of bathtub model to make it really a satellite galaxy population factory, i.e. to make it more capable. One major thing we are adding is a disk potential in the host systems. And to properly assign the disks to halos, we need to know how to use halo properties to predict disk size. That's how it's related. To demonstrate the model's capability, here I show you again, this is what I showed you last year, that subhalo Vmax functions of Milky Way-sized halos can be nicely predicted by this model. Here, gray is model and red is Bolshoi simulation. We can see that above the resolution limit, the model agrees with simulation very nicely, and beyond the resolution limit, the model can easily probe this low mass range, which is relevant for the study of Milky Way satellites. And also, the halo-to-halo variance is nicely probed, which can be hardly done by zoom-in simulations. This is the number distribution, and here I show you the spatial distribution of subhalos, comparing model and Elvis simulation. So what's plotted on the y-axis is actually the number density of subhalos normalized to unity at virial radius, divided by the halo density profile, also normalized to unity at virial radius. So this is, if you want, the bias function of subhalo spatial distribution. And you see, again, very nice agreement. So the next stage of this model development would be to simulate hydro simulations. And to do that, we want to assign disks to host halos. And why this is simulating hydro simulations? The nice work by Shea, Garrison, Kimo may have showed you why this is a fair way to say simulating hydro simulations. And we also want to add subhalo responses to the interactions between subhalos and disks. And for this part, we want to use the simulation provided by Stackenberg. Before I show you the summary slide, I want to very briefly mention another thing we are doing is UDGs in the Nihao simulation. And in particular, I want to show you that UDGs are not a high-spin tail. So here I show you the histogram of all Nihao galaxies, the halo spin parameter. The UDGs are the red histogram, and the non-UDGs of similar mass to the UDGs are the blue histogram. You can see that they follow very similar halo spin distributions here. And UDGs have higher galaxy spin parameter, which is a trivial statement because UDGs are more extended, and more extended means higher spin. So here's my summary. I've showed you that there is almost no spin-spin correlation at high redshift. There may be a weak correlation at low redshift. The galaxy spin and halo and dark matter spin in the inner halo are still correlated. Their alignment is always good. And galaxy spin parameter is higher in more massive halos or post-compaction systems. And we may be able to still predict galaxy size using halo properties, despite that halo spin parameter seems to be irrelevant. And I hope next year I will entertain you more about new results using my SATGEN model. Thank you.
Comments or questions?
About the second point, that's also true for the Nihao simulation. You mentioned this flattening.
That's exactly measured with Nihao simulation. Yeah.
So, do you reconcile that with the flattening as high mass?
The flattening of
the last galaxies don't show that kind of correlation.
It's an issue of Nihao, I think, or generally simulations of a strong feedback. Yeah.
You said UDGs previously have larger spin. I'm not 100% sure because that would require them to be centrifugally supported. They are pressure supported. That will exist at the zero speed. It might still be highly extended. So I don't think that this is a good natural consequence.
No, I actually also checked if the Nihao UDGs are pressure supported. They are. So the V over sigma ratio is of the order of unity, or slightly below unity. So many of them are pressure supported. Yeah.
Aaron?
So
interesting with Williston being irrelevant. There's so many observations that if you just take a really simple-minded model of Williston and allows you to start from the galaxy that matches the observations really well outside of redshift with zero initial scatter. So I'm just wondering if anyone's simulation.
Again, that piece of observation is using abundance matching, right? And enforcing a galaxy size, halo size relation with a scaling on lambda. So what if you use my recipe of relating galaxy size and halo scale radius? You may get equally good or even better matches, I think.
So a comment about halo galaxy spin alignment. So Rock Rosker and Victor just ran zoom-in simulations a few years back, and they noticed that there was a misalignment between the galactic disk and the hot halo. And in fact, this nicely explained the origin of warps in the outer parts of galaxies. Basically, the hot halo cooling onto a different plane gave good results in terms of metallicity and ages of the stars that were formed. So I think those are slightly higher resolution simulations than the NIHA, but
I guess so. But it's also a small sample.
and yeah, I know statistics are really poor. I think at least looking better.
Yeah, sure. Also, TISC showed the other day that some systems are counter-rotating, and it's like 1% of systems are counter-rotating, which is very, very striking. And in our results, it's a distribution covering from anti-parallel to parallel, and it's perfectly fine to have a view. Yeah.
Okay, let's thank Fangzhou again.
Thank you.